Welcome to the 21st lecture of this EMC series. In previous lecture, we have seen how to determine the per unit length inductance and per unit length capacitance of a two-wire transmission line. Now, so we have those results. Today we will apply them to various two-wire transmission lines. The first transmission line that we'll see is a single wire above ground plane. So suppose I have a transmission line of length L and I have an infinite ground plane and the transmission line is connected through a source resistance to a voltage source Vs and this side through a load resistance the thing is grounded, and let us assume that this height above the ground plane of the transmission line is h. Okay. Here easily you see, since the ground plane is there, infinite ground plane, we can use the concept of image theory. Now, as we have already said, the transmission line can be considered as a static problem that we have said. So this thing, that means I can say that basically this whole thing tells me that this transmission line with radius RW and over a height h, this is equivalent to, let us use some other color, this is equivalent to, I have one transmission line, I have H and then another H, no ground plane, and I have this is again image theory, so same radius. So that means I can now say that this so I can say that this is will have a capacitance of 1 and this is equivalent to, this structure is equivalent to C1 another C1 in series and so I can say that this is equal to, so these two are 2H, so in series means two capacitances in series means, so that I can say C2, which is So what is the value of C2? C2 is C1 into C1 by 2C1 is equal to C1 by 2. That means C1 is equal to 2C2. Now already we have found out in the last class this structure, that means two-way transmission line, its per unit length capacitance. So C2 we know, so C1 will be the new one, that means that will be 2 into pi epsilon ln. In previous day it was S by RW. Today S is, how much is this distance? These all distances are 2h. So ln 2h by RW. And its unit will be farad per meter. And we will have to satisfy that H is much greater than RW. So once this is done, we can find out what is the per unit length inductance. Per unit length inductance will be LE is equal to mu epsilon by CE. C is this one. So if we put that, it will be mu by 2 pi ln 2h by RW Henry per meter. So that completes the description of a single wire about the ground plane. So this we'll see later, that many times there will be a single wire, there is a ground plane, particularly in the PCB technology we have ground planes. So a single horizontal wire, above that we know the per unit length capacitance. The next thing that we will now attempt is another very popular structure, that is the coaxial line. You know, coaxial line is very good because it has a good susceptibility. The proximity effect is almost zero, and it's a good differential structure, balanced structure, symmetrical structure. That's why it is popularly used in high frequency circuits. Not very high frequency, because very high frequency requires microwave technology, but between the low frequency and microwave technology, coaxial cable is a very popular choice. This is the transmission line. So we know that there is an inner metallic conductor, there is an outer metallic conductor. The inner conductor is having a radius RW. The outer, then between the outer conductor and inner conductor there is shield. So the shield radius to the inner surface of the outer conductor is RS, and the shield material characteristic is sigma, mu and epsilon. So because of symmetry, how is the field structure? We know the field structure of this. These electric fields are like this because of symmetry. These are all radially outward electric field structure, and the magnetic field is circumferential. Similarly, so how the current flows? The current flows through the shield uniformly. It neither goes inside the inner conductor nor it goes to the outer. So I can say that the current I throughout this, not here. So the current I flows through this, because this is a solid one. So through this the current I flows, and we can say that if we look at this cross section, so then the flux, so if the current is flowing like this, I have a flux, so flux will be Vt, and Vt will be equal to mu into Ht. We know what is Ht. Also actually we will be taking a surface here. This surface is a cylindrical surface. So in that we'll have to take all those, and these things you know, Vt is equal to mu into Ht, and mu is I by 2 pi r. So this total flux by this surface, that we will have to integrate, we will have to carry out this surface integral Vt dot ds. So we will have to have this mu I by 2 pi r dr, because this ds, that will be 2 pi will come out, and r will vary from r w to r s, so it will be 0 I by these two parameters. So this will be mu I by 2 pi ln rs by r2. So LE will be Im by I, that is mu by 2 pi ln similarly so this is the inductance. If you want to determine the capacitance, you can again do this. So we know that Et we have earlier saw it is equal to Q by 2 pi epsilon r. So the voltage between the inner wire and the inner surface of the outer wire is given by V, and V is minus Et dot dl, and why you see the limits, because Rw is at higher potential, that means inner surface is at higher potential than the outer surface. So this will give us Q by 2 pi epsilon ln Rs. So C we can write is Q by V is 2 pi epsilon ln Rs. check. We have found LE into C. So LE was mu0 by this. I am assuming non-ferromagnetic material. So the last is, let us see a problem. Suppose a coaxial cable actually coaxial people, they, or wire industry, they give the things as gauge. So let us say that inner radius aid gauge. Or sometimes they call it mills. So let us say that the for a coaxial cable, the velocity of propagation is 0.66 C. So what is epsilon r? You can immediately see there that just we have derived that V inside a coaxial cable is C by square root of epsilon r. So you can immediately find out that epsilon r is equal to 2.3. Okay. Similarly, if RS and RW given either in inch or in mil or in gauge, you can find out the CR, etc. Okay. So next day we'll see these. Once we have developed the model for the transmission lines, two-way transmission lines, we'll apply that to the final radiated susceptibility model. That we'll do in the next class. mm,